in Sicily, but we'll make the best out of it instead. So this was supposed to be one of the talks of the Poisson conference last summer. So you all see my iPad, I hope. I will write on that, but if you missed something, if I scroll too fast, if I write too fast, I'm giving you a Dropbox link here. So the PDF will be updated, backupped automatically, hopefully in lifetime. And you can just click on the link and go there and scroll back up if you missed something or want to, go back and look at something. Okay, great. So what am I going to be talking about today? So it's going to be the so-called AKSZ construction, which is a tool to, produce action functionals for QFTs originally. And we're going to use the framework of topological field theory, so a very functorial framework. So I come from this math side. And it will be what's called fully extended. I will explain these words throughout the talk, and we'll see. And maybe something that I forgot to write here is that actually, so we will use a version of the AKSZ construction, which is reinterpreted in derived algebraic geometry. And the precise details of this won't be that necessary. I will try to give you as many details about this as you necessarily need for understanding the main goal and the main outcome, but feel free to ask questions about this. So this is joint work with Damien Calaque, who's my PhD thesis advisor, and Rune Haugseng, and has been quite a long time in the making, but hopefully will actually finalize in the next few weeks. Okay, so what's the AKSZ construction? I already said it's a. Let me start. Is the green visible enough? Sometimes people say it's not so visible. Is it dark enough?
It's okay, at least on my screen, but I don't know.
Right. If there are complaints, please complain in the chat. So the AKSZ construction, so this is, I can never remember the names, so I have to read them off. It's Alexandrov, Kontsevich, Schwarz, and Zabronsky. The AKSZ construction is, as I said, a technique for constructing action functionals for QFT, or if you wish, we could also say, well, it's a technique for constructing differential forms, or I mean, this is a Poisson seminar, symplectic forms, and this is the guise in which we will actually see this. So what is happening? We transgress some fixed form along something. So where? So the QFTs that appear in this context are sigma models. So sigma models.
Sorry, Claudia, I have second thoughts about green. Maybe in the future, like this is okay, but maybe in the future.
Okay.
Yeah.
Great, then I'll change the color right away. Let's take purple instead. Okay, sigma models. So sigma models, we have some sort of maps from some sigma into a fixed target. So this will be our target. And this will be somehow our input or world sheet or something like this. And so what's the overall strategy for getting this? So we have our X. This comes equipped with some differential form or symplectic form. And now, if we take our maps, we can actually take the maps cross sigma, and we have a map called evaluation here. And what we will want to do is we will want to pull back our differential form. That's something we can always do. I'm not telling you what geometric objects these are, so this is on purpose. We will talk about this more soon. As a to take away the key message, we will be talking about a situation in derived geometry. So these will be objects in this world, but the overall idea is the same. So we will have a situation, this will be some geometric object. These will be the same type of geometric object. And well, we want to be able to pull back forms. I mean, in most geometric settings, that should be something reasonable we can do. But actually, we wanted to get something on the maps, not on sigma cross maps. So what we will want to do is we will want to push forward along the projection. So this push forward here, you should think of as an integration. And so we need sigma to be oriented of some sort. We want to be able to integrate. Okay, I should mention some examples of such a situation. Where does this actually appear? Where did this originally appear, the original AKSZ construction? So some QFTs where the action function is obtained this way is Chern-Simons theory. There's the Poisson sigma model. There's the Courant sigma model. And I'm sure, I can't see actually the list of the participants, but I'm sure some of them, the main key authors are in the audience here today. And the tool is really, we want to be able to make precise of this pull-push procedure. And for this, we need some sort of a derived geometry input. So that's somehow the underlying setup. So the main tool is some derived geometry setup to make sense of pull-push. And so historically, I mean, it's called transgression. Yes, this is called transgression of differential forms, absolutely. And you need a volume element of sigma. Yes, if we're dealing with manifolds, then that's exactly what we need. Or, I mean, if we're dealing with a setup where we are talking about orientations, then we need an orientation, a choice of orientation. And so we will be working, I mean, my tool, I tried to color code this, I won't be consistent throughout, but the derived geometry that we will use is this derived algebraic geometry setup. And so we will want to be able to make precise of what this type of orientation is, or integrating over sigma is in this derived algebraic geometry setup. Okay. Yeah, so I will try to monitor the chat along the way, but first of all, if somebody else can answer, feel free. So thanks already here at this point, but also if I don't notice, because I won't be able to look up all the time, please let me know if there's a question. Okay, let's start with our first example.
Wow.
Not what I wanted to do.
Yeah, that's what we imagined, right?
Here. Okay. So now I have more space to write. Our first example that we will want to generalize is something that hopefully is familiar to most of you. So we start with sigma unoriented surface and G a reductive algebraic group. So GLN or something like this. And now we want to look at G local systems. So
I'm not sure that there is this question on the chart whether volume is included in orientation, but I guess you can probably also answer it where you have some examples at hand.
Yeah, I mean, I was talking about orientation in the sense of topology. So, but some system where you have a good way of integrating. Let's put it that way. So if you're on a surface on a manifold, then maybe an orientation will be, well, something like a volume element. But so we will, for us, the sigma will really always be some nice manifold. I mean, we will want to have a topological field theory. So the sigma will be some sort of cobordism, so it will be a smooth manifold. So there, by orientation, I really mean some volume form, top dimensional form. Yes. Right. Thank you, Pavel. Okay, so G-local systems. G-local systems, yes. So the simplest way of describing G-local systems on a surface is just by taking homomorphisms from pi1 into G, and then we have to mod out by the G action. So that would be, G-local systems on our surface. But actually, we want to think about not just the set of these things, but we want a moduli space of G-local systems.
Sorry, Claudia, one more question on the chart. Whether the transgression reduces the degree of a form by the dimension of the source.
Absolutely, yes.
Thank
the
you.
integration takes away, so if sigma is d-dimensional, then the integration takes away d degrees.
Okay, thank you.
Right, so we want a moduli space, and by space, I mean here, like I'm in my geometric situation, or maybe let me continue, maybe a different, maybe you prefer G bundles with a flat connection. And maybe for algebraically minded people or representation theory minded people, this is sometimes called the character variety. So it will only be an actual variety or a nice space if this quotient behaves well. But in general, I mean, this is not a quotient that we just take as a quotient, but rather we should do something like a stacky quotient. So we should actually do something like a moduli stack. So we don't want to lose information. I mean, if we want to really have a character variety, then the action of G should be very nice. But maybe more generally, the action of G is not that nice, and we actually have something like a character stack. And this is the first somehow ingredient that we will have in this derived geometry setup, that we will actually be dealing with some stacks. Just to remember, it's 1 hour exactly, right? Is that correct? Yes. Okay, great. Thank you. Okay, so we want stacks instead. And right, but even before we go to stacks, let's say everything is smooth. I said we want to have something to do with differential forms, or maybe even symplectic forms. And these G-local systems, these have the very nice property that they actually do have a symplectic form. It has a symplectic structure. Which goes back to a TM bot. And basically where this comes from is if I take a G-local system, then I can look at wedge 2 of H1 of sigma. Going, well, I just wedge them together. I go to H2. And now my group has, it's a particularly nice group. It's a reductive algebraic group. So I have a killing form. So I can use my killing form here of G. And I get to H2 of sigma valued in C now. And now I can integrate over sigma. So this is a map going from a wedge 2 of something to C. And well, this is indeed actually non-degenerate.
There is a question on the chart asking whether it's related to moduli of flat connections.
Yes, here. It's the moduli space of G bundles with flat connection. Does that answer your question? Yeah, okay.
Well, I guess it should answer the question. but,
Yes.
but of course, Nima, if you want to voice it.
Yeah, great. Okay. Good. All right. Okay, so this is non-degenerate. And the reason this is non-degenerate is, I mean, if we just forget that we had our G here, or let's just look at this part here, then we have Poincare duality of the surface. It's an oriented surface. We have Poincare duality. And well, the killing form is also non-degenerate. This is also non-degenerate. That's part of being a killing form. So this is a killing form non-degenerate plus Poincare duality. Okay, great. So now let's try to see how this relates to what happens over here. We wanted to say something about a pull-push construction. And I claim that this actually indeed comes from such a pull-push. And the thing to note here, and this goes back to, I'll write the names on the next slide, Pantev-Toen-Vaquié-Vezzosi, is that, well, we can interpret all of these things in derived algebraic geometry. Okay, so this here actually, and now I'll try to stick with my blue for the derived algebraic geometry again. This is the smooth locus of a derived stock, which has the form maps of sigma, where now my sigma, my manifold, my surface sigma, I can view this as an object in this derived algebraic geometry, which is called the Betti stack. Just to give you a name, it just remembers the homotopy type of sigma. And my target, X, will be BG. This is the classifying stack. And I mean, this is really basically taking just the topology construction, if you wish, or just taking the nerve of G viewed as a category, taking this as a simplicial set. I mean, this is really a classifying space. This is really what you can think of this. And so now we have it in this convenient form. It looks like this. And my claim is that this procedure of getting this symplectic form on the G-local systems is exactly an instance of this pull-push procedure for this situation.
One more question.
Yes.
Is Nepin stack an Artin stack?
Yes, so that's something one has to prove, but yes. Okay. Good. So let's see. Right. The missing ingredient maybe that I should mention here is that, well, we wanted to understand this as a symplectic form, right? And so the thing that maybe is worth mentioning here is that if I take the tangent of these maps, sorry, this should be big, of course. These maps at some local system, then this is exactly H1 of sigma GL in some suitable sense, okay? So really what this is not just a tangent space, but a tangent complex. And here, the H, this does not sit in degree 0, but sits in degree 1. or -1, depending on your shift conventions, and I will not be consistent. And so that's the sense in which you can really see this, understand this as, okay. Good. So I said I want to say something, right, and I promised you names. So this was by Pantev-Toen-Vaquié-Vezzosi. And this was somehow the motivation for derived symplectic geometry in this derived algebraic geometry framework. Okay, great. So the next ingredient of my talk is we want to talk about topological field theories. So why does this have anything to do with a topological field theory? Well, we can generalize this example to manifolds with boundary. So now if M is a 3-manifold with boundary, and this should be oriented, then we can look at G-local systems on all of M, and those get down to G-local systems on sigma. And this map here now, so remember this right-hand side was symplectic, and this map here is actually Lagrangian. And yeah, do I want to write this down? Maybe I don't want to write this down. And the claim now is that we actually get a topological field theory that is a symmetric monoidal functor going from a category I will call decob to a category I will call lag. And I now have to explain to you what these things are. Okay. So what's decob? My objects are closed d-1 dimensional manifolds, oriented, and my morphisms are d-dimensional cobordisms, and to be fully precise, I need to take these up to suitable diphymorphisms. So we have something like this. This is a morphism from 2 circles to 1 circle, and these are also oriented. Okay, so this is Attia's approach to topological field theories, just defining a topological field theories as such a symmetric monoidal functor. Well, not quite. I mean, Attia's original definition, we had vect on this side, vector spaces and linear maps, and now we're replacing it by something funny. So this is, in our situation, if you look at what my objects were, I mean, if what I explained to you, D was 3, so if D is 3, then, well, to an object, to a closed 2-dimensional manifold, I should assign something on the right. And so what would that be? If you look back at what we had, we got something symplectic. So what about lag? Objects are symplectic, and I'm on purpose not putting anything here. And what should a morphism be? Well, I only told you what happens with 1 boundary, but I could have generalized this to having 2 boundaries, like in this example. So here I can take my M with a sigma in and then sigma out. And then what's my structure? I have G local systems on M, and I can forget down to G local systems on sigma in, and I can forget down to G local systems on sigma out. So this is a correspondence. But the fact that here we had Lagrangians translates over on this side to having a Lagrangian correspondence. So this is a Lagrangian correspondence. So now here comes the point why, one of the points why derived algebraic geometry is useful. So what will composition here be? So composition. So if we have correspondence categories, composition should be composition of correspondences. So I will just abbreviate it here. We are taking the pullback intersection of correspondences, but somehow, usually in a usual setting, if we try to do this with manifolds, for example, this composition just won't always work. It won't always be a Lagrangian correspondence anymore. And that's the convenient thing here about derived algebraic geometry. In derived algebraic geometry, we put a little h over it. So here, we're taking a derived intersection, a homotopical version of an intersection, and then this always works. In this derived algebraic geometry setup. So you can think of derived algebraic geometry, actually one of the main features that it fixes is if you want to start with some algebraic objects, in this case algebraic things, and you want to actually be able to intersect things well. So that's one of the main things that derived algebraic geometry fixes, having well-behaved intersections. So here, this is really now in derived algebraic geometry, if I interpret this here, so that means here I have to put derived stack. So in this case, it's a derived algebraic stack, but whatever. And then the setup is that this is actually really a category, symmetric monodal category. Okay, so in DAG, this was proven as a combination of the PTVB results above here, plus then the TFT idea is due to Damien Calaque. All right, so this is the second thing I want to mention. The third ingredient in the talk now is fully extended topological field theory. So the thing is that cobordisms are very pretty. Maybe I want you to be able to see this. So maybe I'll just start by writing down the theorem that we prove. Sorry. So given, and now there's another ingredient that I haven't told you yet about. So in derived algebraic geometry, we don't only have symplectic things, but we have S-symplectic, S-shifted symplectic things. And I'll get to where that comes from in a moment. X. Then if I take maps from this Betty thing into this fixed X, this is a fully extended d-dimensional oriented topological field theory. Okay, so that's the main result. It's extending this result here to this fully extended version.
Before you move on, there is a question about the previous page. Whether there is an explicit example where composition of Lagrangian relations is bad naively, but is nice in the derived way.
Well, take any example where the naive composition doesn't work. So self-intersection, for example.
Okay, thanks.
Yeah, great, Pavel, thank you. Other Pavel, thank you. Okay. Great. So what's the fully extended here? So now, instead of looking at decobordisms as a category, as a symmetric monodal category, we look at, I mean, this first part doesn't really change much. Now I add my subscript s to incorporate this lag s. That should actually already be here as well. But now these here are infinity D categories. And for the purposes of this talk, I don't really want to go much into detail. Dimension D of the TFT is related to the shift of X. No, it's not. It's actually not. So maybe this is something that I could have said up. Yeah, maybe I'll write it down now. Right. So remark, if X is S shifted symplectic and sigma is d-dimensional, then what PTVV shows is that maps from sigma to X is S minus D shifted symplectic. So it's not related to the shift of X, but to the shift of the thing that appears then. Okay. All right. So maybe this is a good point to say. That means, so in here now, this is a structure, this infinity D category is a structure which does not just include d-dimensional and d-1 dimensional things, d and d-1, but d-2, d-3, and so on, all the way to a point, so to 0-dimensional. So a point here, so this has d-dimensional all the way down to 0-dimensional. And so if you think of what this thing does on a point, so then this will be sent to maps from point to X, which is just X, and that's S shifted symplectic. So if we go all the way down to the points, the shift doesn't appear at the bottom, but it does appear in between for the morphisms. Yes, integration over sigma shifts the degree of the symplectic form. Yeah. All right. So how could we possibly try to prove a theorem like this? So there are two strategies. So the first one is to use a very powerful theorem called the cobordism hypothesis. Which, well, in its first form was formulated by Beitz and Dolan for D categories. And then Lurie realized that one should use these infinity D categories, which I didn't explain to you, but I'm happy to tell you more about if you want to. And what this says is that these theories are fully local. So a fully extended theory is fully local. It's fully determined by what happens at a point. So this is the informal description, fully extended. And then I have to say framed TFT is fully determined by Z on the point. And conversely, can recover Z from just a single object with some properties. Okay, and then plus there is something to you have to deal with to get an oriented theory, but this is not so important at this point. So this is very powerful in the sense that we just have to analyze our object X as an object in this category lag S. And then this powerful theorem will actually tell us we do get a fully extended TFT. However, we won't know that this really looks like this a priori. So the cobordism hypothesis tells us a beautiful existence here, but it doesn't tell us how to actually compute the values on the manifolds. And so, however, why is it called a cobordism hypothesis? Let's talk about this later, okay? So, right. The second strategy, which we will actually do, so we also prove this, it's actually these dualizability conditions, depending on your setting, are harder or easier to do, but in lag S, this turns out to be actually very easy, pretty straightforward. What's much harder is to actually explicitly construct this. So I won't tell you exactly what I mean by infinity D category here, because it's actually not so important at this point. I can show you why this is annoying or hard to construct, even without telling you the precise definition of an infinity D category. And so the goal for the rest of the talk is to showcase an instance of why this might be annoying or difficult to do, not just straightforward. Okay, good. All right, so maybe it's worth to take a minute to actually show you one example of an S-shifted symplectic form before we actually go into the details of why this theorem might be not straightforward once you unravel the definitions. So to get back to our main example, we wanted to think about X being BG. So our example that he bought symplectic form, we had the mapping stack with the fixed target here being BG. So example of, in this case, 2 shifted symplectic. So we take X to be BG, that will be our main example. And now the tangent in this derived algebraic geometry framework of BG is just the Lie algebra shifted by 1. So the cotangent is just G dual shifted by -1. And so here it's really important we have these shifts here. So that's something that we don't see in normal geometry where we just have a tangent space. We really have a tangent complex here. And the shift is the crucial ingredient. And so what does it usually mean to have a symplectic form? Well, we have some identification of T and the cotangent. So but I mean, this here is a chain complex concentrated in degree +1, and this one is one concentrated in degree -1. So, well, I will never have an isomorphism here, right? But as chain complexes, or even quasi-isomorphism, there's no way I can get that. But if I actually shift this by 2, well, then I do have this. And this is just the killing form. Okay. This is in fact even an isomorphism here, but quasi-isomorphism would suffice. And so this shift here, this 2, is the reason for my 2 shift in symplectic. Just to give you an example why this appears. All right.
May I ask a question?
Yes.
So the killing form is non-degenerate only if G is semi-simple. But could you take here any quadratic Lie algebra and an invariant non-degenerate bilinear form and so get a 2-shifted symplectic form?
I want to say yes. I mean, as soon as you have this non-degeneracy present, yes. I'm not entirely sure how to interpret this then as a stack. I think that's then more the problem. But maybe we can talk about this after the talk.
All right, thank you.
Okay. Great. Maybe the other example that I want to give you is what happens if we have maps from sigma to some x. At some point x. Well, this will just be the singular cochains. Oh, I wanted to take the example BG here. No. Sigma BG. And then we just get the singular cochains here. And so now in this situation, the symplectic form here, remember that was our theorem from PTVV, was that this actually has a symplectic form. Then this, if sigma is oriented, then identifying singular cohomology and homology is just Poincare duality. So that's the reincarnation of what we saw before.
There is a question on the chart whether it's equivalent to looking at Cartan's 3 form and Alan Weinstein's 2 form, or there is also some other model for BG. So how is it?
I don't know the answer to this.
Trying to help Claudia to answer her question. So someone were asking what was it Claudia said she was not sure about what's on the stack, and I think that's on the stack.
Okay, thank you. All right, how much higher coherence? Well, at the moment, I didn't tell you anything about higher coherence. And I'm going to tell you exactly why higher coherence is shows up in a moment. So the naive thing you would like to have if you have a symmetric monoidal functor is, well, I mean, if you have a functor, you want that if you take the source and the target, that there are some diagrams that commute. So to check that something is a functor, you usually have to check that some diagram commutes. And the problem will be in the naive first approach of how to define these things. These diagrams won't commute, but just commute up to homotopy. And that's exactly where coherences come in that Theo is mentioning, and that we have to incorporate as data instead of just saying up to homotopy to really get a functor of infinity D categories. Okay, so the two steps, so for 2. We have yet more 2 steps. So we will factor our functor into 2 parts. We will put something in the middle, which I will call oriented D. And then we go to lag S. Okay, so this first part, the idea is basically you just chop bordism into the pieces. So what I mean by this is that I want to get a co-span or co-correspondence. So eventually we want to end up with some correspondences on this side. So I have to get some co-correspondences in between. So I mean, naively, this sounds very easy. So what we do is if we have something like this, then we just get the inclusion of the boundary pieces. Or if I have a composition of 2 such things, then what I have on the other side is a more complicated diagram, namely something like this. Okay, so that's just basically this first procedure. The first half of this first procedure is to extract the diagram, just because, I mean, these are the diagrams that will appear in this lag side. But they have more. Namely, they are, so first of all, we need to make stacks out of them. We need to apply this mysterious functor Betty that I told you about to get stacks, so that we're in the derived geometry framework that we want to use. And these have to be oriented. So there is a notion of what an oriented stack is. And actually, these have to be oriented cospans. So in particular, if I have a stack, so these are formulated as, so first they're formulated as taking the singular chains, which appeared in our example here. So it's not surprising that they will appear over there. These are somehow the ring of functions in my setting of M. Going to, and now we're in the setting of having chain complexes everywhere. So we have a map of chain complex as this. And this is just capping with a fundamental class. So this is on objects. But now what happens on morphisms? So we really want to have everything being functorial. So hopefully this is also formulated in a way like this. And before I tell you what this is, I forgot to tell you that we will actually, maybe I'll use a different color. Actually, we like integrating. So we replace this by de Rham forms just for convenience. And then we just do integration, just because we like integrating and we know how to do that. Okay, so our orientation, our oriented cospans are encoded by this integration map. But now what happens on morphisms? So on morphisms, I have, well, I mean, I told you that I'm reformulating the things in terms of these cospans. So I have to tell you what an orientation on such a cospan is. So yeah, I have to go down. There's no hope. Okay. So on morphisms, what do I want to have there? So if I have some, what did I have? My convention was M and then a sigma in and a sigma out. So for example, something like this. So on the forms, I have maps going the other way. And so one might hope that we can just integrate everywhere. Okay. But the problem is that this diagram won't be a commuting diagram. Well, I mean, this is an easy calculation you can do. If we integrate over omega, well, restricted, and we integrate over the outputs, they're not the same, right? But instead, Stokes' theorem tells us that there's a difference, which is exactly the integral over d omega, right? So this is, in particular, this is not zero in general. Oh, all right. So the problem is if I look at these diagrams, they don't commute, but somehow, I mean, our framework suggested, I mean, we are looking in these Lagrangian correspondences always as commuting diagrams. So if we want to go to this middle part here, this will be defined in terms of stacks together with such structure which commutes. That's the natural thing to do, to be able to then just map over to our Lagrangian correspondences. But it doesn't commute, it only commutes up to homotopy. And so we have to modify these frameworks. The naive first definition of what to put here doesn't work. That would be with these commuting diagrams, but we have to actually modify this to allow for these extra non-commuting things. And so that's difficulty in defining this as a infinity D functor, simply because we have to add these pieces. So what's our strategy now? Well, our strategy so we add space to include the data of this homotopy. In this case, it's this integral over dm. Okay. So what is this in practice? Let me take my diagram here again. So what we will do in practice is we'll erase these. And now this goes over here. This goes over here. So I added some space in the middle. And so in the middle, I can add something. My integration from omega of m will not go to just k shifted by minus d, but instead it will go to k shifted by minus d plus k shifted by minus d minus 1. So this is another chain complex. And I have maps. This is quasi-isomorphic. So I didn't really change much. At the bottom, I just replaced my constant thing, k shifted by minus d, by now changing the middle term. Yes. And so, elaborate what this is. So what's this k plus k going down to k? So this takes an x comma y and sends it to y minus x. That's my chain complex in the middle. And what's this map in the middle? Let me call this red now. What does my red map do? Well, it takes an omega in here and sends it to, here I integrate over the in part and I integrate over the out part. And I have a second component, which is integrating over the whole thing. Okay. So this gave me my map going to this bigger chain complex. And now if you check what happens, it actually does commute. It actually does work. And we didn't change much. We just replaced this bottom diagram with something bigger. But this replacing it by something bigger allowed us to include our homotopy. I think there's a D missing here. Okay. So this is the first example of why this naive integration would not give us the coherent diagrams that we want. And in infinity categories, unfortunately, you have to keep track of all this stuff. But altogether, well, you can do this and add a lot of data and add a lot of coherences and fiddle around with it for a while, and then you get the actual functor. So the second part here, and then I'm done. This second part here, this really is this then once you put a lot of work into this guy in the middle here, this is not tart anymore. This is really just applying maps into your fixed target. So the tricky part really is this first part. Okay, thank you very much.
Well, thanks a lot. So questions or comments? Yeah, Alejandro.
Yes, thank you. Thank you for the talk. I have two questions. One is about the non-algebraic case. In the case where the X that you were taking as a target, not an algebraic stack, so then the mapping stack would be maybe infinite dimensional. I don't know if you know about this.
I didn't hear the last sentence. Then the mapping stack is?
It's infinite dimensional.
Infinite dimensional. Mm-hmm.
Yeah, so, or maybe, I don't know, but do you know how to deal with this case?
So I personally don't. However, the main tool here really was to have a derived geometry set up that was somehow stable enough to make sense of these ingredients. So we needed to have things like our mapping stack is an Artin stack. And then we can define a tangent complex, we can define a cotangent complex, and so on. So there are, as soon as you have a setup of derived geometry where you can do that, then you would be able to do the same procedure as we do. So this is maybe an advantage of somehow the way we set this up here, that the second part, I mean, that will just be straightforward and easy. And in here, it's from our construction rather clear which elements you would need to replace with a good derived geometry setup. So I know that one of Damien Calaque's students has been working on one of these derived geometry setups, some sort of a derived smooth geometry setup suitable for this. And Pelle Steffens, and I think he's graduating this year, so hopefully his thesis will be available soon.
Okay, thank you. And the other question, it's about computation of examples. In the first example that you mentioned, you could try to compute the Poisson invariant, for example, of a closed free manifold. But the question is if the extended picture, so in general, you would chop this free manifold, cutting it along surfaces and then compute intersections.
Yes.
But does the extended picture simplify this computation or give it another flavor somehow?
Well, of course, that's ultimately somehow the thing you want to do with fully extended TFTs, that the fact that you can decompose it into very simple pieces allows you to recover and recompute. However, in practice, I mean, these things are not that easy. You certainly can start trying to compute the derived intersections that appear on this side, and hopefully if your situation is easy enough, then you can recover some things. The other thing maybe that's worth mentioning here is with the Poisson invariant or something. I mean, here we really end with these like Lagrangian things, right? So usually the invariants, the TQFT invariants, you would then want to go to some like a quantization or something to get something linear. So that step is certainly missing here, right? That's not there.
And have you tried to see what this yields for the Poisson sigma model? Computing some of the intersections or?
No, I have not. No.
Okay. Thank you.
You're welcome.
Thank you. Theo?
So thank you for the great talk. So my question about higher coherence was in the definition of symplectic, of shifted symplectic form. And I was wondering if, so I guess the longer version of the question is, should I worry that there's, I mean, is it possible that there, for sort of some subtle coherence data to be, that I have to worry about, maybe taking advantage of other terms in the algebraic homology or something? Does this ever happen?
I mean, giving a symplectic structure, I mean, I say structure it's a lot of data. I mean, I've completely swept under the rug. I only told you about 1/2 of the story. So what you need is a so-called closed two form plus non-degeneracy of the underlying two form. So closed is not a property anymore, but is actually structure.
And in the case of BG, is it possible for that structure to be surprising?
No. So BG is just, I mean, this higher closure structure, there's only one and that's unique. But there are situations where you might have different closure structures.
Oh, okay.
Yeah.
And presumably there's like a calculation I could do that would show me it was unique if I knew how to do it.
Yeah.
Okay. Can I,
well, this is basically because the tangent is just concentrated in 1 degree. There's like nothing you can do really.
I had the other question, but I think you answered Alejandro already, and it was sort of the same. It was if there's like, is it plausible to imagine a kind of Bordism category for Calaque?
Yes.
For like,
actually,
actual Calaque varieties rather than these Betty stacks.
Yeah, actually, I mean, that's something one could do. One could replace, so then the thing that you really want is the second part of the functor. If here you replace this by some Calaque threefolds or something, yes, you could do that. I don't know how to exactly encode cobordisms in this language, but yes, one should be able to do that. Certainly manifold with boundary is easy to replace in that situation.
More questions or comments? I got a somewhat naive question, and maybe some other people in the audience should be asking it, but see, following on Alejandro's question about when you chop a manifold into pieces and you would like to then assemble back maybe some invariants, right? There is this program by Cataneo, Neff, and Dreshetikin, where they are trying to do it within some Batalin-Vilkovisky field series. Superficially, the words sound similar. Like how similar or how different, or what's the relation between these two programs? Is it?
So I think currently it's unknown. Pavel, maybe you want to add something to that, but certainly the ideas, I know that Damien Calaque got like the idea for this project by listening to Alberto giving a talk about their project and their program. So thank you very much for this comment. It's, I think, really helpful. So at present, I'm not in, I think coming back to this question about using different derived geometry setups, I think that's one of the deficits at the moment for why I don't know how to link these things, because in their setup, certainly having the more of the manifold than just a homotopy type is important. So that's certainly one instance of the things where I don't know how to resolve at this point. But the ideas, certainly that's the strategy is very similar, but uses very different tools for this classical part that they had a couple of years ago. And then there's the quantization part, which is not present at all in our picture here. There is one thing to be said, though, if you now restrict here, we really have, in the Lagrangian category, we really have some derived stacks. In this higher category, if you restrict to a linear piece of this, then Owen William and Rune Haugseng, one of my co-authors here, they actually have a BV quantization functor going to like at least for, they don't have the Lagrangian correspondences, but with like the homomorphisms, then going to algebras and EN algebras more generally. So, but there, that's even further from how I would ever understand relating to what Pavel and Claudia and Alberto do, because that's a very different language and very different framework. But certainly there should be a relation there.
Okay, thank you. More questions or comments?
Yeah, hi. And I have an elementary question going back to the beginning of your talk. Mm-hmm. So sigma was a compact surface without boundary.
Yes.
But if it has boundary, then, we know that this moduli space is going to have a Poisson structure instead of a symplectic structure. Mm-hmm. So this procedure that you describe of pulling back and then doing integration along the fiber, what is going on there then? Is there some replacement for that you can do with, I don't know, direct structures or something?
So I think there should be, there is a notion of Poisson, shifted Poisson structures in this derived algebraic geometry setting. Pavel Safronov is here somewhere in the audience who's an expert on this.
What confuses me is the fiber integration part. The pullback looks good, but the fiber integration, how would that work?
Yeah, I don't know how to answer that question, because the second half of what I was going to say is that there should, in principle, be a replacement, but there isn't at present. Pavel, do you want to add anything? Do you have any comments on this? Is he still here? I don't know. He was here before.
I guess he wrote something on the chat.
Yeah.
In the chat, yeah.
Okay, if sigma has a boundary, maps from sigma bg to maps to the boundary has a one-shifted Lagrangian structure.
Yeah, I could also read it.
Great.
This is answering the question. The Poisson structure you mentioned is a part of that Lagrangian structure that Claudia is talking about. So Claudia would say that you have this restriction map, which is Lagrangian, and there's a general result that if you have any, in this case, one-shifted Lagrangian map, on the source you have a Poisson structure. Mm-hmm. And that's the Poisson structure, you know, on the character variety.
Mm-hmm.
Thank you. That was helpful. I had totally misunderstood the question.
Okay, thank you.
Oh, thank you. More questions or comments? Well, if not, Claudia, thanks again for a great talk.
Thank you very much. And I really hope to see everybody soon in person again.
Well, thank you everybody for participating today. And next time we'll have Vladimir Fogg speaking on global Poisson. So, well, thanks again, everybody, and see you next week.
Thanks, Anton. Thanks, Claudia.
Bye. Thanks.
Thanks a lot.